Yes, Krishna, where were you? I think you have not attended the classes, 2 to 3 classes, no? Last
Yes, ma'am.
exams
I
were
was
going
having
on.
exams.
Okay,
Yes,
okay.
ma'am.
So how did your exam go?
Yes, ma'am. It went well.
Krishna, send me your physics question paper on WhatsApp, okay?
Okay,
After
ma'am.
the class. So when will you approximately receive your answer sheets?
Ma'am, I have already
You have
received.
received. Please share me in the chat box your score. Okay, Krishna.
Okay, ma'am.
All right, class. So we have started with, okay, one more thing. Krishna, what was the syllabus of physics that came in your school? So that much part would be prepared for you. How many lessons were there, Krishna?
Ma'am, the first book was whole except the last chapter.
Whole book, first book, or complete physics?
Yeah, except the last chapter.
Communication system.
No.
Semiconductors. Semiconductors.
No, ma'am. I'll just tell you, ma'am. It's okay. Ma'am, except electromagnetic waves, there were all other chapters.
Okay, okay, except for EM waves. Till Zen in your school, you both are not in the same school, no? Zen and Krishna.
I don't think so.
He is telling his syllabus. Okay. So second book also, Krishna, has been completed in your school.
No, ma'am. They just started.
They have just started. No, so first book is completely done. So I hope first book from your part is also now revised because of the exam.
Yes, ma'am.
So electromagnetic waves, you had already given the test. So first book should be prepared by now for you, Krishna. And yes, Krishna, share your score as well. All right. Because I have to know what's your progress in school as well. No, right now I only know about the scores that you're scoring here. Okay. So it's a good score. It's a very good score, Krishna. And overall percentage, Krishna? Overall score, this is just for physics, no? Overall. So Krishna.
Still few papers are remaining.
Okay. Some paper showing is left. Fine, Krishna. You are at which place, Krishna? You're not in India, no?
No, ma'am. In Saudi Arabia.
Okay. Others also, as soon as you get your scores, no, whatever is your score, do let me know. Because accordingly, we'll have to plan revision classes and rest of the thing. That's why I'm asking you all. Okay, so Heinz principle we had started and main principle we have completed it. So Krishna, you have to take up the recordings. All right, do take the recordings from me. Text me on WhatsApp because now I'll start with interference today. And Heinz principle part, I think it will be difficult for you to tally up. Okay, so please get your backups clear. Take the video lectures and get it clear.
Okay, ma'am.
So Heinz principle basically told us what? This told us that source is there. Source produced a primary wavefront. The primary wavefront had sources on it, point sources on it. The sources acted as the fresh source. The points on the primary wavefront became the fresh sources for the secondary wavefronts. So each point on the primary wavefront developed secondary wavefront. So all the forward envelopes gave you the next wavefront. Similarly, this wavefront will have point sources. It will form secondary wavefronts. Its forward envelope will form one more wavefront. Like this, the wavefront will keep on propagating, and the forward propulsion of the wavefronts is given by the Heinz principle mainly. Now, two questions that come from your exam. See, from Heinz principle directly, either this part can be asked to you in your exam, final board examination also, as well as in your school pre-boards also, it can be asked. For writing this part, it can be a state Heinz principle, but more than this, the types, we did prism, convex, this part. This is important part. This can be asked to you directly. So whatever we have done, as it is, you have to write it in your exam. All the devices we have done, convex lens, concave mirror, everything we have done. So from here only it comes. And two more things that come from Heinz principle. Either reflection, to prove reflection on the basis of wave theory, that is your Heinz principle, or to prove refraction on the basis of wave theory, that is Heinz principle can come. So either it can come, and usually refraction has appeared more in the exams, but reflection can also come. Reflection has also come in your exam. But when you are revising, refraction has the frequency of refraction part coming in your exam is more. So I'm just telling you whatever has come. Now reflection on the basis of wave theory we'll do, then refraction on the basis of wave theory. That will complete your Heinz principle, and then we'll start with interference. Now these two parts are also important because, as I've told you, as it is directly, this will be given to you. Let's say I have taken a plane mirror. Fine, I'm taking a plane mirror. Some M1, M2, this is mirror is there. M1, M2, this is a mirror. Now what will happen? Incident ray will fall on it. Ray of light will be incident on it. As per the laws of reflection, what will happen? A ray of light will get reflected. A ray of light will get reflected. So this is normal simple because of the normal, this was the incident ray and this is the reflected ray. This is the incident ray and this is the reflected ray. This is the incident ray. And this is the reflected ray. Now, in the last class only, I have told you that the wavefront is always perpendicular to the rays. Rays are perpendicular to wavefront. So perpendicular from here, no, at an angle of 90 degree. Let's say this is some A. So at an angle of 90 degree, I think this is not appearing 90, no? At an angle of 90 degree, because incident rays are perpendicular to the wavefronts. So this is your incident wavefront. This is incident ray. And this becomes your incident wavefront. This is incident wavefront. Let's say this is some A point. So incident wavefront makes angle of I with the mirror. So this becomes angle of incidence. This is the angle of incidence of wavefront. You can see this is the incident wavefront now because this angle is 90 degree. So this is angle of incidence. Now coming to the part that we have actually studied. Now coming to the main Heinz principle that is involved. Now what will happen? The way we had drawn prism and all the convex lenses, concave lenses, all the ray diagrams for the prism and all the lens in the last class. Now what will happen? Let's say this is some point B. So because of A point, since A point is nearer, what we'll do? We'll be having a secondary wavefront because this point will act as a fresh source for the new disturbance. Similarly, point B will also act as a fresh source for disturbance. Let's say this is because of point B. Secondary wavefronts have been drawn because of the primary wavefront. This is the incident wavefront. Now the forward envelope according to Heinz principle will give you the reflected wavefront. So this becomes the reflected wavefront. Now what will happen? Incident ray, this is a reflected wavefront. Now incident ray, it's not only a single incident ray that must have arised over here. What will happen? An incident ray will be incident here as well. Incident ray will be here is incident here as well, the way it was incident over here. And it will get reflected. Again, it will get reflected perpendicularly. An incident ray will come. That incident ray will give rise to the next wavefront. Similarly, again, incident ray will be there like this. This will keep on propagating. And Heinz principle is used. Some B point, let's name this also. B dash, this point as A dash. And this completes, since this is the reflected wavefront, so this becomes angle of reflection. This is the angle of reflection for the wavefront, angle of incidence for the wavefront. And see, speed is V, let's say, because same medium is there. So speed into time, this will be the distance. Means this and this. Let's say this is point A, not right. Because wavefront is formed here, no? So this is point A, not this. Wavefront is formed over here. So this will be the wavefront. Now coming to the part that we have to prove. We have to prove the fact that angle of incidence is equal to angle of reflection, and all these three lie in the same plane. So all these three lie in the same plane has been proved through the diagram, through the ray diagram only that we have drawn, all the rays. This is proving that yes. But how to prove angle of incidence is equal to angle of reflection? Now see carefully. Look at this triangle A dash AB, and look at this triangle BB dash A dash. This triangle and this triangle. Incident ray, this angle A and this angle B dash, both are 90 degrees. Why? Because wavefront and the rays both are perpendicular to each other. Yesterday I had told you on this Tuesday's class. So this angle is also 90 degree. This angle is also 90 degree. Fine. B dash, the reflected ray, this is equal to VT, and A dash, this is also equal to VT. So both are equal. It means you can say this triangle and this triangle both are congruent. If two triangles are congruent, so what happens? All the sides become equal, all the angles become equal. They are not similar, they are congruent triangles. So this is 90 degree, this is 90 degree. This is VT, this is VT. It means this side is equal, this side is equal, this angle is equal, this angle is equal. Once you have proven that the triangles are similar, it means this angle also is equal to this angle. This side is equal to this side, that you can see because both have this common side. So definitely this is same. VA dash and A dash B is same. VT same. 90 same. AB B dash A dash same. So I is equal to R. So firstly we had proved how to prove this. See, you will write in both the triangles. Firstly, you have in the triangle A dash and triangle B dash A, both the triangles. Firstly, it was observed that B dash was equal to A dash, which was equal to VT. Fine, speed into time. Also, A dash was equal to A dash, common side. This side was common, no? And angle A was equal to angle B dash. Both were equal to 90 degree. So SAS similarity, congruency, this proves that triangle BAA dash is congruent to triangle BB dash A. If this is the case, then definitely angle of incidence will be angle of reflection. And this is what this proves, your laws of reflection. And all these lie in the same plane that has already been depicted by the ray diagram that has been drawn. All right, class, this is if question comes, prove reflection on the basis of Heinz principle or wave theory. Copy as it is in your paper. Copy means whatever has been written, remember it as it is. This is enough. We'll do refraction, note it down first. Now see, that was reflection. So reflection was proved. Now refraction on the basis of Heinz theory. So refraction is occurring. So same thing. Mirror, let's take, not mirror, we'll take some interface where one side, let's say this side is medium 1, which is rarer. This is second, this is denser. Refractive index is N1, refractive index of this medium is N2. Now, incident ray will fall. This is the incident ray. Normal will be there. Now what will happen? Perpendicular to the rays, there is presence of the incident wavefront. So this is incident wavefront. Incident ray, this is the incident ray. There's a difference between the rays and wavefront. Incident ray. So incident ray, incident wavefront. Fine. Now this point, let's say A point, this point, let's say B point. What will happen? Heinz principle. This will also become the source for the new wavefront. Let's say here. This point is very close, so a little closer. We'll be having it. Now let's see. Somewhere here it will fall this way. Like this it will fall. Now see, look here. If the incident ray is incident and this is a rarer medium, this is a denser medium. So what will happen? Reflection will not occur here. Here what will happen? Here you will see refraction occurring. Fine. Let's say this intersection is some B dash I've taken. Now one incident ray will definitely not fall. To show now what will happen? This much part has occurred. Now incident ray will be incident at this point. Now what will happen? Again, refraction will occur here. A normal will be drawn. Refraction will occur here. 2 points will be there. Secondary wavelets will be developed because of the incident light. Secondary wavefront will be developed. And then again, same, this process will continue, whatever we have studied for Heinz principle. All right, let's name this also some A dash. So this is now angle of incidence because this is angle of incidence. Because this is incident wavefront and this is your plane surface. So angle of incidence of wavefront. Incidence. Incidence. And this is angle of refraction because this is the refracted wavefront. No, this has been refracted. The forward envelope, because of Heinz principle, this has been refracted. So this is refracted wavefront. And these are the normal refracted rays. Now see, here no, when I'll write VT for this ray and when I'll write VT for this ray, see in the previous case when I was writing reflection, what happened? In case of reflection, there was a single medium. So speed for the entire wave in that medium will be same. Now medium is different. One is rarer, one is denser. As you can only see directly, because here refraction is occurring. So if refraction is occurring, that means definitely velocity is changing. So if velocity is changing, I cannot write it same. It means this is, if this is V1t, this has to be some V2t. So V1 is speed in first medium. V2 is speed in second medium. The refractive indexes are N1 in first medium, refractive index is N2 in second medium. Also, since you can see this is this incident ray and this incident ray, both are reaching at the same time. Time is same, no? It means this has a higher speed. So V1 has a higher speed than V2. Now, how will you prove this? If you see this triangle, see this will be perpendicular. Incident ray and wavefront both will be perpendicular to each other, right? If this is perpendicular and here this will be perpendicular. Now see, if you take sine I from here, sine theta, that is sine I. So this will be perpendicular divided by hypotenuse. So perpendicular is A dash or V1t you can say. divided by BA dash, right? V1T by BA dash. Similarly, if you see sine R will be perpendicular it will be perpendicular divided by the hypotenuse. So perpendicular is here BB dash. If it is BB dash, if it is BB dash divided by BA dash, so V2T divided by BA dash, right? Sine theta will be perpendicular divided by the hypotenuse. Now see. So firstly, if you see in triangle BAA dash, sine I will be equal to AA dash by BA dash, and AA dash was V1T by BA dash. Similarly, in the second triangle, that was BB dash A dash, BB dash A dash. Sine R was equal to BB dash by BA dash. So BB dash by BA dash. BB dash was equal to V2 by BA dash, right? Now let's take their ratios. Sine I by sine R. Sine I is what? V1T by BA dash into. Sine R is V2T by BA dash. So BA dash cancels, T gets cancelled. So this is equal to V1 by V2. And we already know V1 by V2 is equal to N2 by N1. So from here, you have your final answer. Sine I by sine R is equal to N2 1. So this proved what? This proved us Snell's law. So Snell's law, first statement has been, so since incident ray and all these lie in the same plane, laws of refraction are these only. All these lie in the same plane can be shown by the ray diagram. Now tell me, any doubts in reflection or refraction on the basis of Heinz? This is just a proof. No numerical will come from here. It is just a proof that you already know the answer for this. You are proving it using the wave theory. You are implying you're just using your wave theory. You're not using the lenses or the mirrors to prove the refraction or the reflection. This is simply the refractions proof. Any doubts? Is it clear to all of you till here? Fatima, Hanifa, clear?
Yes, teacher.
Season. This is the incident ray. It got refracted here. All right. Now, perpendicular to the incident ray, you have the incident wave front, right? Now, what happened? Point A acted as the fresh source of the new disturbance. So, point A gave rise to this secondary wavelet. Point B will also act as a fresh source of disturbance. So, it also gave rise to this secondary wavelet, fine, wavefront. When I joined it, though it had to be like this, just make this. When I joined it, I got the refracted wavefront. Fine, this is because why refracted? Because refraction is the medium has changed, so definitely this is refracted wavefront. Fine. Now incident ray will come again here. Again, refraction will occur. Similarly, incident wavefront will be perpendicular to here. Again, 2 points will give rise to secondary wavelets. Again, it will form a refracted wavefront. Then again, incident wavefront will occur, and this way propulsion will keep on occurring, and Heinz theory will be there. Is it clear till here? This part is clear, how the ray diagram is formed? All right. Derivation, did you understand, or should I repeat once the derivation part? Then. Oh. Zayn, your mic is on by mistake. Okay, class. So that completes with the Heinz principle. Uh, let's take a break of 5 minutes, go through the lesson. If you have any doubts from this chapter, let me know. After the break, I'll clarify your doubt. Then we'll start freshly from interference. So take a break of 5 to 10 minutes. Yes. Then we'll start with interference, which is a completely new topic from Okay, now before we start with interference, see, interference and diffraction, both of them have some properties that are similar. So certain topics that we are going to do right now, that will be common for both diffraction and interference. Now interference and diffraction, only these two topics are left for you. As I've told you, polarization has been deleted in your syllabus. So just interference, this topic, and one more topic, diffraction, is left. For both of these, you have a common topic, that is to understand the wave equation. Now see, wave equation is already the wave equation that we have discussed. And this was a part of your class 11 syllabus also. Just revising it. Equation for displacement. So Y here depicts the displacement. A represents the amplitude. Amplitude is the maximum value of displacement. Sine is normal trigonometric function sine that is present. Omega is angular frequency. T is time. All right, minus we already know that it shows us the direction of the wave. K is angular wave number. This, why am I doing it fast? Because we have just done it in electromagnetic waves only. So angular wave number. Angular wave number has a relation with the wavelength. What's that relation? How do you relate angular wave K with lambda? Any formula that we did? K and lambda, we had done a formula. Yes, K is equal to, not new, 2 pi. 2 pi by lambda. Good, Zen. K is equal to 2 pi by lambda, not new. New is frequency. That is for velocity, and that too even multiplication. So K is 2 pi by lambda. Nx tells you what? X basically tells you position of the wave. The rest of the things, same things, no need to repeat the point. Just now we have done electromagnetic waves. Recently we had done it. So electric field, magnetic field, and the direction of propagation all are perpendicular to each other. This was also discussed. Wave equation is there. Now the next topic that will be used in case of interference and diffraction. Again telling you this is common to all. Phase and phase difference. So phase difference is the same phase difference that we had studied in case of alternating current. Phase difference between current and voltage. So phase difference is what? Phase is the angle. Fine. This whole term, this entire term, omega t minus kx, this entire term is known as phase. Fine. This entire term is known as phase. Now what will happen? If you take the differences of the two phases, from one equation, one phase, from second equation, second phase. If you subtract it, you get the phase difference. For example, one equation, I have written it on the screen. Y1 is equal to A sine omega t. Second equation, I have written as A sine omega t plus phi naught. Fine. Now, when I subtract it, I want to find out the phase difference. So, phase for this equation is omega t plus phi minus phase for the first equation. So omega t gets cancelled. Phase difference is equal to phi naught. So in the equations directly also you can write phi. For example, here the phase difference. So y1 is equal to a sine omega t plus pi by 4. Y2 is equal to a sine omega t plus pi by 2. So if I want to find out the phase difference, this is one phi naught. This is the other phi naught's value. So I'll subtract these pi by 2 minus pi by 4. This is equal to pi by 4 only. So this becomes the phase difference. It means pi by 4. So if one wave is there, other wave is also present, the phase difference between them will become pi by 4. This is y1, this is y2. This is what is meant by phase difference. So firstly, meaning of all the waves, what all the terms represent the waves. Then secondly, the phase difference. Phase difference means the angular difference between the waves, how the waves differ in the angles, by what amount one wave is ahead of the other, or if they are not overlapping to each other. It means some angle will be there between the waves. That is known as phase difference. After phase difference, you get one quantity, that is path difference. Let's do path difference, then I think you can note it down. See, phase difference is the differences between the phases. Path difference becomes the difference between two parts of the waves that has been covered. For example, I have taken a screen and two slits have been made from where I have projected two waves. So waves are flowing from here. This is one wave, this is another wave. Path difference means if S1P, see S1P, this is the path of this wave, and S2P is the path of this wave. If you overlap it, there will be some remaining portion that is known as path difference. Or you can say simply path difference is what? It's the difference in both the paths. So if I have to write path difference will be equal to path difference. I'm depicting it as X. This will be equal to S2P minus S1P. So this is equal to S2P minus S1P. This is the path difference. Means S1P is the path of the first wave, S2P is the path of the second wave. So the difference, it means if I take S2P and if I take S1P and I put S1P on S2P, there will be this remaining portion. This is the path difference. Now there's a relation between the path difference and phase difference. Relation between path difference and phase difference. So phase difference, that is phi naught, or let me write it in words first. Phase difference by 2 pi is equal to path difference. Remember this formula for the complete optics, wave optics. So that is phase difference phi naught by 2 pi. This is equal to path difference is x by lambda. Use this relation wherever required. And this relation is the most important relation. Everywhere this will be used. You have to find out the path difference and phase difference at all the points. Fine. So phi naught by 2 pi is equal to x by lambda. For example, if we take the same example, phi naught is pi by 2. Put it here. Pi by 2. This is phi naught. Here 2 pi is equal to x by lambda. Pi gets cancelled. X equals to lambda by 4. Understood? This is what is path difference, phase difference. Two more quantities before discussing interference. Firstly, note it down, then we'll discuss. So, two more topics before we start with diffraction and interference. Superposition principle we did. What was superposition principle? In electrostatics, we have done superposition principle. Yes, what was superposition principle? Two waves superimpose each other with the same phase. No, this is for the waves. I'm asking in general for electrostatics. Good, Zen. But what about the other students who have had the classes? Krishna, Rishan, Fatima. No idea of superposition principle.
Ma'am, sum of two or more waves which overlap each other is.
I'm asking in general, why are you focusing on waves? We did superposition principle for forces. We did superposition principle for different potentials. What was that? I'm asking you what we have already studied. Not for this waves, I'll tell you. Yes, Sarah, Krishna, Huzefa. What was the statement? In terms of force, only tell me, or in terms of potential, tell me. Fatima. Superposition principle. Hamza. Hiba.
Ma'am, vector sum of all the forces with respect to direction.
Was what? The net force was given. No, superposition principle did what? If you had n number of forces, then resultant force was given by superposition principle. You people have not revised superposition principle ever. How have you all appeared for your exams then? In electrostatics, it was repeated so many times. For forces, net resultant of the force was given by the vector addition of all the forces. In case of potential, the net resultant was given by algebraic addition of all the potentials that were present. Superposition did what? If you had more than a single physical quantity, the resultant was given by adding it. And if it's a vector quantity, it was vectorically added. If it was an algebraic scalar quantity, it was algebraically added. Here also, if you have a number of waves that are traveling, and if they superimpose each other, so each wave will be having its own displacement or not. Resultant wave, each wave will be having its individual displacement. If you want to find out what's the resultant displacement, that will be given by simply adding all the displacements. So let's say y1 is there, y2 is there, up till let's say n number of waves are present. So resultant displacement will be simply directly if you will add it. This is the superposition principle here in case of waves. But you are not even remembering, none of you could answer it, superposition principle. Now the next topic before, as I was telling you, this is important, is coherent sources. So in case of coherent sources, what happens? Let's say a screen is there, one source is there. Now this wave is generated and the wavelength of this wave is lambda and the frequency is nu. And there is one more source, S2. This wave got generated. This wave is also having wavelength lambda and frequency nu. And the phase difference, let's say the phase difference is continuously phi. So these type of sources, no, which emit the waves having same wavelength, same frequency and a constant phase difference. These types of sources are known as coherent sources. And if somehow your phase difference becomes variable, or the wavelengths differ, or the frequencies are different, then you see those sources which are emitting such waves, these are known as non-coherent sources. And your interference phenomena is completely valid for your coherent sources. That's why we are understanding coherent sources. So two independent sources cannot be coherent path, because path difference can be variable for it. So if path difference is variable, then non-coherent sources. So wavelength, frequency, same, exact same, and constant phase difference. The phase difference, so that will be there between the wave. It should not happen that initially the waves are at 90-degree perpendicular to each other, then the path difference increased between them and suddenly decreased. No. Path difference, if it is pi by 2, it should remain pi by 2. If it is pi, it should remain pi. That is, these types of sources are known as coherent sources. And waves have same wavelength and frequency. All right. Note these points and we'll start with interference. Now see, interference is what? See, when these waves no superimpose from such sources, if the sources are coherent sources and the two waves superimpose each other. For example, this is one wave and this is another wave. So both the waves are superimposing on each other. So when this superimposition has been done but produced from the coherent sources, then that phenomena is known as interference. All right. But that is just for your understanding. If it comes in the exam, then you have to mention this definition. This one. This is important for your writing, for your exam point of view. But understanding, no, this is it. This is exactly what happens in interference. So phenomena of redistribution of light energy, whatever is the light energy, means from the sources, energies or particles have been emitted. This is what is meant till here. So phenomena of redistribution of light energy due to superposition of light waves from two coherent sources. So superposition of light waves from two coherent sources is interference. Coherent sources, this is a very must condition for interference. If it is not coherent sources, then interference does not occur. Now you have an experiment that is known as Young's double slit experiment. So Young's double slit experiment is the most important topic from interference as well as from your complete wave optics. In the entrances also, a single question definitely comes from Young's modulus, YDSC experiments there are. And even in the previous years, you'll find the maximum questions from Young's double slit experiment only. And most of the time from interference, this Young's double slit experiment is used. In your numericals also, you will find in YDSC experiment, this happened. In YD experiment, that happened like this. Now, what is YDSC experiment? Young scientists, you must have heard of this name earlier also. Young's modulus, you must have heard of in your mechanical properties of solids. So the same scientist did what? He used a source and he took two slits. This you can see this is one slit and this is another slit. You have single slit experiments as well for interference, but we have Young's double slit experiment that what we are discussing. Now the separation between both the slits is small d and this is a screen. Now what is happening when the source has emitted its waves? Waves travel from both the slits, but what is observed is see, waves will superimpose each other because of superposition principle. When the waves, one wave's crest and other waves trough. Trough. So when one wave's crest overlaps with other's crest and other's trough overlaps with the other's trough. Like this is also known as constructive interference. When this occurs, the fringe that you form, or what you'll see like this, some bright light, a sort of rectangular bright light you'll see. That is the region where the waves have constructively interfered with each other. That is, crest of one wave overlap with the crest of other wave. Trough of one wave overlaps with the trough of another wave. Since the intensity increases, so you get a bright fringe. And at certain places, what will happen? Crest, trough with trough and crest. This will also occur. So in such cases, you'll observe dark fringes, not even gray colored, complete black. This experiment you can also perform at your home. Comb, comb you have. So from the comb, if you have the comb's brushes are like this, just leave two slits and cover the rest of the comb.
Teacher, your camera is on.
Yes, Fatima?
You were explaining something, right?
Yes. My voice is not audible.
No, it is audible about the comb.
From here, this. From here, I'm explaining, Fatima. Okay. From here. Are you able to look at this? In the corner of the screen. Just have a look. Here I'm explaining it.
Oh, yes, yes.
Okay. So if this is the comb, let's see, leaving two slits. Suppose this part I have covered it. This part I have covered. This is the middle part. I have covered this, and this is the part that I have covered. So two brushes of the comb I have left. And if you use a laser light, no. So through these slits, laser light also if you pass on, then you will observe exactly at certain places you will see like this. Bright fringes will be there. And at these places you will see dark fringes will be formed on the screen. So this experiment you all can also perform at your home. And even in some students have to perform in their investigative projects. Some students take up projects from different chapters, like from Coulomb's law. Some have like this. Prism students take. So from Young's double slit experiment and also single slit experiment, students take up the topic. So they usually have this. So Young's double slit experiment was this only. This was done by Young's. Now you have a derivation. Let me write it down, then you can copy it so that rest of the things will be there. Now see, main equation of resultant wave is there. But if by chance, see this derivation which I am writing, no, coming of this derivation in the exam is a little less, chances are there. This is the equation of resultant wave due to superposition. So I'll tell you, see, your equation is A sine omega t. Second equation, let's say this is A sine omega t plus phi. This is some phase difference of it. Find certain phase differences there. Phase difference, again telling you, this phase difference is phi. Now intensity, one more relation. See, intensity is directly proportional to square of amplitude. So intensity of the first wave will be, and this proportionality sign will get removed, a constant will be there. This will be K A square. Similarly, intensity for the second wave will be K. Let's change the amplitude because we are not sure about the amplitude. No, how can we say both the waves have the same amplitude? Let's make it some B. This is B and K B square. Now using superposition principle, Y will be simply Y1 plus Y2. So add it, A sine omega t plus. So Y becomes A sine omega t plus B sine omega t plus phi. So this is sine A plus B. So how can we write this? A sine omega t plus B. We can write this as sine A cos B plus cos A sine B. Like this we can write it. Now let's multiply B with both. So Y will be equal to A sine omega t plus B sine omega t cos phi plus B cos omega t sine phi. We can do one thing. Sine omega t we can take constant. So sine omega t. What is left? A is left from here if you take out sine omega t. So A is left. From here, what is left? If sine omega t is taken common. From here.
B cos phi.
B cos phi. Only Krishna is attentive. Or what in the class? From here, B cos phi will be left. And this is what? This is B cos omega t sine phi. So I'm writing B sine phi together. B sine phi cos omega t. Fine. Now see, this term, no, A plus B cos of phi. This term, A plus B cos phi. This is written as R cos theta. This is the resultant. R is the resultant of the wave. and theta is the phase difference resultant. And this term b sine theta, b sine phi, this is written as r sine theta. See, r is what? R is amplitude of the final resultant wave that we'll obtain. And theta is what? Theta is phase constant of resultant waves. Phase constant. Phase constant of resultant wave. Fine. Now let's substitute these values, r cos theta and r sine theta. So sine omega t a plus b cos theta was there. So I'm writing it as r cos theta. Fine. And b cos phi, b sine phi cos omega t was there. So I'm writing sine theta cos omega t. Just these values I have substituted. So if we take r common, or let's write r like this: r sine omega t cos theta plus r sine theta cos omega t. Right? So y is equal to what? This is r sine. See again, can you see the identity with which we have started? Remember, which we have started with what we are trying to prove, the final equation. Sine a b plus, see from here, if you take r common, r won't be here. This is sine a cos b, sine a cos b plus sine b cos a. So that becomes simply sine a plus b. So omega t plus theta. This is the equation of the resultant. So if it comes equation of resultant wave, equation of resultant wave. This can be asked to you to derive. Fine. Note all these parts. Any doubts you have, let me know. The rest of the things we'll continue in the next class. Young's double slit is easier to explain, Hamza, because the theory portion is very less, so you can rote learn and remember all the theory part that is present. And to demonstrate also, the equipments that are needed is very less. For the Wheatstone bridge, no, you have to ensure that the circuit is working or not. It can happen that due to any loose connection, your project can become weaker, and the questions can be trickier for you in Wheatstone bridge. Like if we interchange it, then what will happen? And everything get related to your complete current electricity. And giving Y of current electricity is difficult as compared to giving Y of wave optics. From wave optics, you have to remember and understand interference completely for giving the investigatory project of YDSC. So from the easier perspective, you have, I think YDSC will be better. And the experiments equipments are also much not needed.
Can you scroll up? Done, ma'am.
All those who have completed, you all can leave now. Thank you so much, class. We'll continue this on Tuesday now.
Thank you, ma'am.